How would you go about working whether an arbitrarily large number is square? There are a couple of ways we could go about this. We could just think, okay, what are the square numbers that are close to this? And does this land on one of them? Of course, as we get larger and larger numbers, that's going to get more tricky. Then we could also try and prime factorize this to see, do each of the prime factors have an even power? Because if they do, that would necessitate the number being a square. We could go ahead and try and do this. So 5,924, and we can just keep dividing by 2 until we can't divide by 2 anymore. So that would be 2,962. We go again, you get 1,481. Now we look at this and like, it ends in a square. The last 2 digits are a square number. So we're like, okay, it's looking promising, but it's not going to be divisible by 3. We can test divisibility by 7, but it's clearly 81's not divisible by 7, so that's not going to work. And then obviously not divisible by 5. I just skipped that. But I'm going to have to keep going through all these prime numbers until we figure out, okay, what this is divisible by, which is not easy. And there's the possibility that 1,481 is actually prime, in which case this would not be square. But we're going to have to sit here for a while testing this, and it would be much nicer if there were a faster way to do this, which there is. So when we look at this, we can consider a modular arithmetic table and consider this mod 3. Now, I'd recommend just writing down different modular arithmetic tables so you know when you're dividing by 3, dividing by 4, dividing by 5, what the remainders are that could make that number a square, okay? I'll show you exactly what I mean. So if we divide, or if we consider multiplying numbers in the mod 3 world, and this is going to be the one that's useful for this. Whenever we're dividing by a number by 3, we've either got remainder 0, remainder 1, or remainder 2. Now, if you have a number with remainder 0 and you multiply it by another number with remainder 0, then there's like multiplying 2 multiples of 3 together. When you divide that by 3, it's still going to have a remainder of 0. And that's the case in these as well. You multiply a number by 3, regardless of the remainder of the other number. When we divide it by 3 again, the remainder is always going to be 0. So multiplication in our modular arithmetic world of remainders happens exactly how we expect. 1 times 1 is 1, 1 times 2 is 2, 1 times 2 is 2, 2 times 2 is not 4 in this case, it is 1, because it's 1 more than a multiple of 3. So if you look at this diagonal, our square numbers will always be on this diagonal. They'll either have a remainder of 0, a remainder of 1, or that's it, another remainder of 1. So you can't have a remainder of 2 and mod 3 and the number be square. Now, if we look at 5,924, we can sum the digits to figure out the remainder, mod 3. So that's 6, 11, 20. So it's the same as 20 mod 3, which is the same as 2 mod 3. 2 more than 18. So this has got a remainder of 2 when divided by 3, but we've just shown with this table that it's only possible when dividing by 3 if the number is square for it to have a remainder of 0 or a remainder of 1. So therefore, this number cannot be square. Now, this won't always work in the mod 3 world. Sometimes you get a non-square number which does have a remainder of 0 or 1, but then you can also test whether it works mod 4 or mod 5, besides just mod 10 when you know that every square number has to have a last digit of 1, 4, 5, 6, or 9. So that's like the mod 10 version, essentially. So yes, it gives you more ways to test and check whether or not a big number is square or whether you're just wasting your time trying to prime factorize a number which is in fact prime. Let me know if this is a useful technique in the comments.